Today we're going to be talking about Taylor's theorem, or error bound. And error is basically how close is our approximation to what the actual sum of our series is. So if you were in class with me, we'd be filling in this table, understanding that this series here is really that series. And that sum, since we're geometric, you plug into the geometric formula and you get 2/3. So the first partial sum is 1/2. Error, which is the actual sum minus our partial sum, the absolute value of that is 0.16. Repeating. The next term's value is 0.25. Now I'm going to continue filling in these values, but I want you to recognize that our error is under. So our approximation is under the actual next term's value. Plugging in 3/4, 0.083, repeating. The next term's value is negative 1.25, which now this is above the value. Next, 0.625. Our sum is 0.0416. Our next term's value is 0.0625. And this is under our approximation. 0.6875 is our next partial sum, with our error being 0.02083. The next term, negative 0.03125. And now this is over. So we have an over approximation comparing to our next term. So we're next 101.10416, and this is an under approximation because our next term is 0.015625. So what we're doing is, for a decreasing alternating series, you're trying to get to your sum and you keep flopping between. So sometimes you're above the sum, sometimes you're less than the sum, and you keep flopping back and forth when we're dealing with an alternating series. So our function, the actual sum, is the approximate value plus the remainder. So the remainder, or the error, that's what the term we're going to be using. The error is the absolute value of the function, all the function values being added up, minus the polynomial. And how we find that for an alternating series is, if your Taylor series is alternating, so jumping from positive to negative, you're going to find your error in the next unused term. So that's why in the slides I was talking about what the next term's value was, and how our error was jumping between above and below. So error is maximized, so the right side here, left side, this means error. Okay, so the error is maximized in the absolute value of the next unused term. Okay, let's do an example. Let me flip to my example. Okay, so approximate the sum by using the first 6 terms. So just plugging in 1 minus 1/2 plus 1/3 factorial minus 1/4 factorial plus 1/5 factorial minus 1/6 factorial. And when I add those all up together, I just want to look, I got bunch of notes happening here. I just want to make sure I have it right. Yep. 0.63194. Find the upper bound for the remainder. So meaning the rest of the series. So what's the maximum the rest of the series is going to add up to? And that is found in the next unused term. So that's in my 1/7 factorial term, which ends up being 0.000198. So I need to find the upper bounds and lower bounds of the actual sum. So since our series alternates, this is what we said the sum is for the first 6 terms. I can subtract the remainder to get the lower bound, and then we add the remainder to get the upper bound. So I know that our sum is going to range somewhere in between there. Okay, approximating that with an error of less than 0.001. So start listing out your terms. So 1, okay, I go to my next term 1/2. That is still greater than what I want my error to be. My next term is 1/4 factorial. Which is still, so this is 0.0416. So this is still greater than what I want my error to be. So I keep listing my terms. 1/6 factorial. So that's 0.00138888. And then there's like an 8. I think, actually, no, the 8s go on forever. So this is still greater than what I want my error to be. So I go to my next term. This error is less than that value. So that's the one I cross off. So this estimates that with an error less than 0.001. Now we want to look at this. What elementary series is that? Or one of our common series. I call these the common series. Which common series does that look like? Where I'm alternating between positive and negative numbers. Well, that's cosine. What's the x value we have plugged in? The cosine of 1. The cosine of 1 is 0.54030. So I wonder if I added those up. I'm just doing this on the fly. When I add up all those terms, I get 0.54027 repeating. So if I subtract cosine of 1 minus my previous answer, I get what the error is, and the error ends up being 2.4528 times 10 to the negative 5th. Well, if you think about it, that number is definitely less than that. So we've approximated cosine of 1 with a bunch of terms. Now, what if your series is not alternating? We use Lagrange error bound. And what this means, okay, so it's for a non-alternating series. So this is the value of the derivative, where this value of the next term's derivative is a maximum value. And I'll talk about that in a few of the problems. And then you're going to be using C is typically your center. X is the X value you're probably trying to approximate at. N plus 1. So really this is using the next term. But what you have to keep in mind is this value here, this is the maximum value that the derivative could be, the next maximum value the derivative could be. Okay, so let's go through an example. Hopefully once I do an example, this will make sense. So estimate e to the second with for the Maclaurin polynomial of degree 10. So e to the x is everybody in. That's my crazy way of remembering it. Dot 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 plus all the way x to the 10 over 10 factorial. Now, what is x? X is 2. So I'm really looking for it should be a 2 there. Okay, so that's my estimation. So I'm going to say estimation. Use the Lagrange form or error. So I go to the next term. So I go to the 11th term. And the derivative of e to the x is e to the x. So e to the 11th, the value of the derivative x to the 11th over 11 factorial. Technically here I should have x minus c, but our x was 2 and our center was 0, so I just left that as 2. So you can leave it like this. If you plug it in your calculator, I bet you that's going to be a really small number. The calculator might even say 0. Okay, our next example. So the fifth derivative of some function is 700 sine x. And if 0.7 is in the convergence interval for the power series centered at 0, find the upper limit for the error with the fourth degree Taylor polynomial that is used to approximate 0.07. So my Lagrange error bound is less than or equal to the absolute value, the highest value of my derivative, times by the x value we're trying to approximate at minus our center to the fifth power. Since it's fourth degree, I go to the fifth power all over 5 factorial. Now, all of this is pretty easy, I think, ish, except for this value here. So what's the maximum value? What's the maximum value of that derivative? The maximum value of that derivative is 700. But let's look up here what our graph looks like for sine of x. Close to 0. Here is about 0.7. So a little bit better of a Lagrange error bound would technically be the value of the derivative, so 700 sine 0.7. Okay, the actual value of the derivative, 0.7 to the fifth power, all over 5 factorial. So our Lagrange error bound, so this is the maximum, our error is going to be less than or equal to that. Okay, our next one. So if the sixth derivative is a positive decreasing function, find the error bound for a fifth degree Taylor polynomial centered at 4 is used to approximate 4.1. So again, our Lagrange error bound. Let me use this color. The value of the sixth derivative and then the x value you have minus your center. Since I'm using the 5th degree, I'm going to the 6th power all over 6 factorial. So, simplifying that a little bit, we need to know what value I plug in here. I have a positive decreasing function. 1, 2, 3, 4. So what is the maximum value of the derivative? The maximum value of our derivative is actually the value of 4. I don't know how to find that value, but this is the most that I can say. And we use 4 here because that's the maximum value the derivative can take on. Okay. Next one. Let's use this color. So write the first 4 series and the general term. Okay, e to the negative 2x first 4 terms. Okay, good. 2, 3 factorial. Since I'm centered at 0, remember I can just use that general Taylor series formulas that we derived in class. Find the maximum error for the 4th degree polynomial. Okay, so my 4th degree polynomial, I go to the 5th term. So my 5th term, the value of the 5th term, sorry, I got distracted. The value of the 5th term. So highest value of the derivative, x minus 0 to the 5th, all over 5 factorial. Now, where did I get that? I got that from here. Remember, those coefficients, that coefficient up there, that's the highest value of the derivative. That's where I got distracted. I was like, where do I get that negative 2 from? That 2 comes from the 5th derivative. 5th derivative, the coefficient of the derivative, remember, is this number that's on the top. So, now what I'm trying to do is I'm trying to find the maximum error. So I have in here negative 2 to the 5th. Now basically what's the range? I'm going from, the center is 0, but I'm going to negative 0.1 and 0.1. So 0.1 minus 0 to the 5th over 5 factorial. When you put that in your calculator and take the absolute value, you get 2.667 times by 10 to the negative 6th. Okay, last example. Ooh, this is a long one. It's going to be interesting trying to teach this tomorrow in class. Okay, function defined by this power series for all real numbers x. Show that approximate f of 1 with an error less than 10 or 1 over 1000. So 1 over 3, so what term do I go to? I go to my next term. So I go to this next term. Okay, I plug in 1. When I plug in 1, I get 1 over 120. Well, that's going to be less than 1 over 100. So that's showing me that this approximates whatever function, crazy function this is, f of 1, with an error less than 1 over 100. Okay, that is error bound. I apologize if you're not in my class. If you're in my class, hopefully this kind of clears up questions you may have had during class.